That was almost perfect timing. All right. So last time we left off on this is alkane sources. Typically, most alkane sources, actually basically all 99 point something percent of alkane sources, or really organic compound sources, come from petroleum currently. Okay. It gets a little bit more complex if you count recycling as not petroleum, but if they originally came from petroleum, I would count them. But the world feedstock, do you guys know what feedstock is? Okay, it's what you use to make other stuff from. So basically almost all of it comes from petroleum sources, fossil fuel sources. Okay? There is actually a bunch of research that's being done right now to try to change that, but we are decades away from replacing in any way that makes any sense for cost. Okay? And many of these processes would actually be worse for the environment. Currently. I mean, long term they could get much better, but anyways, how do we separate out the different components of our petroleum? Well, we do what's called fractional distillation. We'll end up doing a distillation in lab, but we won't fractionate it. You kind of do this if you ever do a distillery, like a moonshine operation. It actually is done in 3 fractions, right? So that would be a form of fractional distillation. This is a much faster form of fractional distillation. If you look carefully, you can see this refinery has towers that it either stages out and lets things cool down from the different towers, or it will have multiple outlets on a tower where it's taking fractions off depending on height. Okay? And what they're doing is the things that boil really well, because they're very light, right? They're very short chains, will come off on the top. Okay? The things that don't boil as well will come off in the middle, and so on. And so that's literally the different fractions they get off of petroleum. Natural gas, gasoline, butane in between there, gasoline, diesel, motor oil, etc. Okay? Okay. And then the stuff that's left down at the bottom would be like asphalt, tar. Anybody have any questions? All right. Typically, these do not actually emit a lot of fuels or gas or anything out of them. If you ever see anything being emitted out of the top, it would be a flame that they're using to heat it. They're burning some of the fuel to do that. And typically, they would be pure white because they don't want to burn the higher density stuff because they're trying to get that, right? Okay. I did forget kerosene, by the way, which would be like jet fuel and stuff. But anyways, you got the idea, right? All right. If you guys ever end up in Ohio, they have a lot of this, okay? And really huge ones, like you can see them for miles upon miles. You can drive for 50 miles and still not make it around it. Okay? Massive. Okay, so this is the catalytic cracking and hydrocracking. So this is catalytic hydrocracking here. And so here we have a long chain alkane. We're going to expose this to H2, hydrogen gas, and heat in the presence of a catalyst. Notice the name, catalytic, with catalyst, right? Hydrogen, cracking. What are we doing to it? Cracking it, right? We're going to split it into 2 parts. If you ever hear cracking, I'm going to crack a ring. I'm going to crack this compound. That means we're splitting it up, okay? Making smaller compounds from it. And so in this case, we're going to get shorter chain alkanes. In this case, we get a C5 and a C7 out of the C12 chain. Notice here we have catalytic cracking. What's the big difference here? No hydrogen. You got it. We didn't supply it with excess hydrogen, and so we don't have enough hydrogens for them to be fully hydrogenated, right? Okay. Fully substituted with hydrogens, right? And so what ends up happening when we crack it? Well, we need to make a double bond, don't we? Okay.
So why wouldn't you split it down the middle, like cracking it from UC6?
The stability. Yeah, it's more stable this way. This is not something you're going to just be doing willy-nilly like this. This is one of the most common products from doing this, but most cracking with something like this that's a long chain, you'll get multiple products from. You won't just get two. Okay? This is just one of the possible reactions you could get from it. And I'd have to look at these to see if these are even one of the more stable ones, to be very honest with you. This could just be what they felt was a good one to look at. It happens. The double bonds location is actually due to stability of where a double bond is most stable, if you're ever curious.
So we'll just have to look at that and be able to know which one added
This is actually just an example of this reaction. And you'd be given something if I was ever to ask a question on this, like, I show you this, what is this? Okay. Like, there isn't enough information here yet to be able to go through and do the reaction. Yeah. And if you look at the reactions where I would actually have you generate products and reactants, I always give you some sort of hint in that of what sort of chain links, okay? Like this sort of thing where it's just blank and it all looks the same, there's not really anything that differentiates any of these bonds in here. Okay? It could have been any of those. And yeah. Plus, we haven't even learned about hydrogenation or any of the other reactions. This is literally just coming in because we just talked about cracking. Right? We just talked about distillery and yeah. This is how you get the different chain links of the different hydrocarbons. Okay? If you ever wondered, like, how do we get certain types of diesels and certain mixtures of gasoline and all that stuff? This is how. We take the fuels that we get and we can crack them to get the other ones. Okay? Depending on if you care if it has a double bond or not, you may have to do hydrogenation as well. Okay? All right, so this is actually your distillations. You could have guessed this just by looking at the table I gave you previously. Remember where I had you look at that table with the links of different hydrocarbons and their boiling points? Guess what these numbers correspond to? That table. Right? So these are just that table. That's all they are. You're literally just doing a normal distillation. It's just things come off in bands, and they don't typically separate those bands because they're too difficult to separate unless they have to. Okay? And that has cost associated with it if you're curious. Anyways, this right here under 30 degrees, boiling point, boiling range, I should say in this case, is the stuff with 2 to 4 carbons. Anybody know why the 1 carbon one isn't in there? That's methane gas, and you actually would have to freeze it under 0. Yeah. So it'd be very difficult to freeze, so they basically don't dry. Okay? That's also why natural gas is mostly methane, in case you're curious. Right? We get 1, 2, and 3 carbons are typically the most prevalent natural gas. But it's like in a house. Anyways, that's heating gases usually. This right here is gasoline. It's typically the stuff between 4 and 9 carbons long. Not necessarily straight chain. It can also be branched. Just the overall molecular weight. This is going to be the fuels you use in most cars. This is kerosene. This is, well, you can see, look at like a kerosene heater or kerosene lamps, but mostly it's used for jet fuel. Okay? It burns very, very hot, but it burns differently than gasoline. It doesn't quite have that get up and go because it doesn't have the low vapor pressure, so it can vaporize easily. Diesel. Anybody ever driven a diesel vehicle? No? No?
I didn't drive.
Uh-huh.
But I've been in one.
Okay. So like you get more miles per gallon with diesel because it has longer chains, so you can burn more, right? Okay. It has lower volatility though, so if you press the pedal, there's a little bit more time until it starts going. Because it doesn't have a volatile fuel, that means it doesn't go in the vapor as easy. Okay? Anyways, this is heavy oil here. That's for the heating and lubrication. By the way, anybody ever seen petroleum jelly? Like things like Vaseline, that sort of stuff? Yeah, that's that. This is the paraffin wax. You know, the wax that you can put on stuff? Okay. And there's asphalt. Notice this just says residue, and these actually require vacuums to possibly boil. Okay? Okay. All right, so...
What is petroleum jelly used for?
Usually to lubricate stuff. Yeah. Basically, that's the big thing. It also can help maintain moisture inside of something.
Aren't they used for like old school bombs?
Huh?
Aren't they used for like old school bombs?
Bombs? Like boom?
Yeah.
I mean, you can make a bomb out of gasoline. Yeah. Mostly these things aren't used for bombs because number one, like back in the day they were, and low tech wise they are. Like people make Molotovs out of gasoline. But Molotov literally is just a bottle of gasoline and then a flaming object strapped to it. That's it. Okay? And they use those as bombs a whole lot in 2020. Probably too soon for that one, but that's not actually a bomb, by the way. There's a distinction between bomb and other explosives. Bombs have a pressure chamber, okay? That's why, like, the Boston bomber used a pressure cooker. Is a bomb, you are going to combust something. It's going to cause pressure to build up. You'll have a pressure containment device that will then fail after it reaches a very high pressure. And that causes a sudden explosion, like a rubber band. Stretch out the rubber band, get tension on it, bam, right? Okay. Whereas most explosives just react so quickly that they expand out in the cloud while they're still reacting. And that's why they have less a concussive force. Does that make sense? Okay. Yeah. And so these typically would be used for things that are explosives, but not bombs. You can use them for bombs, but they're not quite energy dense enough usually. These technically would be energy dense enough, but they'd be very difficult to actually ignite quickly. They have a slow ignition, which is the problem here. That's why you don't see, like, kerosene you can absolutely use as a bomb. They did use it as a bomb in a very famous attack on U.S. soil. Yeah. That's why they crash planes into things. Jet fuel. It's technically not a bomb, but yes, an explosive. This stuff, they don't typically use it as bombs simply because the ignition isn't fast enough. They did use it as flamethrowers, and that's what napalm was. Yeah. But those are actually against the Geneva Convention. Were against the Geneva Convention before the U.S. used them in Vietnam. Just for everybody's clarification there. You know that the United States has actually violated the Geneva Convention on hundreds of cases since it was created, right? Yeah, there actually is not a major nation that has upheld it completely. So, yeah. Anyways, we'll get off of that. Chemistry. Okay. This right here is methane, by the way. It is tetrahedral in its shape. Everybody remembers tetrahedral, right? 4 objects pointing off of it, or 4 domains, 4 areas that electrons are occupying. And the maximum separation for 4 objects pointing in different directions is that shape right there, tetrahedral, right? Okay, this right here is the space filling. See that they actually represent the same thing, just in different methods, right? These would be the normal bond angles and distances for those hydrogens around the carbon. 109.5 degrees would be a perfect separation, right? To make that shape, you have to hybridize your orbitals, and so you end up with an sp3 hybridization, don't you? Okay. Anybody know why you have to hybridize your orbitals? What would the p orbitals look like? X, Y, Z, right? They'd be 90-degree separations. Okay. And that's because you have 6 domains for the p orbitals, don't you? Not 4. Okay? Okay. Excuse me, 8 domains, not 4. Okay. Here's ethane. You can see that all ethane is it's 2 sp3 hybrid carbons bonded together, 2 tetrahedral shapes. They have to be offset from each other because if they were perfectly aligned, they'd end up bumping into each other, right? Can you see that? Like if this was aligned with this one, they'd interact, wouldn't they? Okay. Kind of like, why do you have to offset your fingers when you put your hands together? Can you put your hands together by not offsetting your fingers? Yeah, you're doing it. Good. Yep. And you got it the other way. You can't put them actually through each other, can you? No, they repel. Okay, so once you get to 2 or more carbons, you have something that's called conformations. You have multiple options for how these can line up, right? Just like your hands have multiple options for how they can line up. That is conformations. And see the conformations, the exact definition your book gives you is conformations are different arrangements of atoms caused by rotation around a single bond. Remember, when you're looking at conformations, you're going to look down a bond, a single bond, and see how they're lined up against each other. Okay? That means there are multiple conformations when you have multiple bonds that can have conformations, right? Okay. These are the conformations for ethane. Ethane being the simplest molecule you can have that would have conformations, right? Well, the simplest hydrocarbon you can have that would have conformations. Okay, so in this case, what we have is we have these sp3 hybridized carbons. They have this pyramid shape, right? And so what's going to happen is you can have rotation around that single bond. Put your 2 fingers together. Can you rotate your thumb one from the other? Very easily, right? Why is that? Because one object you can rotate around very easily, can't you? Remember, a single bond, all it is 2 electrons pulling those 2 nuclei together, right? So that nucleus can freely rotate around, that molecule on the other side can freely rotate around, okay? And they do. They're constantly spinning around in comparison to each other, okay? Most of the time that doesn't really matter much because you have 3 hydrogens here, you can't really tell the difference between them anyways, right? Okay. But once you start substituting stuff, you can tell the difference, can't you? Okay. Okay. And so yes, there are 3 different rotations here that would give you 3 different conformers. They just aren't distinct. Another way of saying that is they'd be degenerate, right? Because they'd all have the same energy. Okay, so this is a Newman projection. This is the easy way to think about and discuss conformations. So remember, the definition of a conformation is it is the rotations around a single bond, right? If I want to easily think about the rotations around something, do I look at it from the side? Can I discuss the rotations of an airplane propeller very well from the side? No, it doesn't make any sense, right? So what do I do if I want to talk about the rotations of an airplane propeller or any rotations around an axis? I look at it down the axis, don't I? And that's called a Newman projection when you do that for molecules. Okay? And so this right here would be the ethane we were talking about, right? And see how it's opposite sides for that hydrogen's there. All the hydrogens are on opposite sides from each other. See that? Okay. Does everybody remember the wedges, what they mean? Okay, what does this dark wedge mean? Yeah, it's coming out towards me, right? What does this dash mean? Yeah, it's going away from you into the paper, right? Okay. What does the solid line right there mean? It's in the paper, the plane of the paper, right? It's not coming away or towards you, it's flat. Okay? Okay. Okay, so you take this ethane, the black one's going to be the one closest to you, okay? You look down so that the black one right here, this carbon, is going to overlap the pink one. Okay? Okay. Newman projections by format are going to have the front carbon as a infinitesimally small dot. So it's just going to be where all the hydrogen bonds join together, that's your carbon. Okay? The rear carbon you draw as a circle. So this right here would be the rear carbon. Everybody see that okay? Okay. So what's this point right here? Yeah, that'd be the front carbon, right? The rear carbon is the circle, right? And keep that in mind, they're going to be perfectly lined up in a Newman projection. So the centers are, basically they're the same thing. You just can't see them both, right? Okay. Okay, so the hydrogens that are attached to the front carbon are going to be represented by bonds drawn out. So the hydrogens are outside the circle, right? You need to do that because otherwise you can't tell what the hell they are. All right? Okay. The rear carbon's hydrogens are the ones that are attached to the circle but do not draw through into the middle. See that? Okay. Okay. Can everybody see why these are the same thing? See that? We look here. This hydrogen is this one here, isn't it? Can everybody see that okay? This hydrogen is that one, isn't it? Okay. This one right here, the dash line, is that. Solid wedge, that. Okay. Okay, so try to practice actually rotating this. This is where those three-dimensional models that I asked you to go ahead and get, but not require, really, really help out, okay? The computer program can kind of help a little bit, but not a lot, right? Does anybody have any questions about this so far? What are those called again? Newman projections. You got it. Named after somebody, by the way, who came up with these. But I'm not going to go into a long history lesson because that's just not necessary. Okay, so the ethane conformations. Here we see the different conformation of ethane. What you're literally looking at is, this is that same potential energy diagram you've seen for many other things in chemistry, right? We do that a lot, okay? And the reason we do that is, what is a low potential energy? Well, that's stable, isn't it? And so we'll spend most of our time in those forms, won't we? High potential energies mean that it has a very high motivation to fall down, doesn't it? It's like putting it on a precarious shelf. It's going to fall. Okay? It's probably not going to take that long. All right. Okay, so again, remember that these are going to be the high energy portions. Okay? They're typically called transition states. Okay? Because they're going to transition through them. They're high energy, so they're going to fall down to conformers. Conformers are the ones that will be more stable, and so they're the ones we'll see more. Conformers don't all have to be the same energy, but in this case they are. Okay? And that's because we have the same thing 3 times, right? Okay. This right here would be the angle between 2 of the hydrogens we have labeled for this purpose. Okay? So these 2 blue hydrogens, see those ones? Okay, we have labeled those for this purpose. In reality, if we want to do this, we could do something like substituting deuteriums on there. Okay? Literally making those something that weigh differently. Okay, and so what's going to happen is at 0, they're going to be lined up, right? That's the highest energy because they're going to interfere with each other, right? So they have electron clouds that will repel. Okay, so what happens as we get off of that 0? They're going to get separated and more stable, right? Until they hit 60 degrees. What's magic about 60 degrees? Yeah, that's in between these 2 hydrogens, isn't it? So we have 60 degrees on both sides. Why is that? Well, what's 360? A full circle. 360 is also 0, isn't it? Okay. And so 3 120s is 360, isn't it? Halfway between 120 is 60. Yeah. Okay, this is typically called the staggered conformation, but it also has other names if those different conformations matter. Okay? There's subdivisions of staggered. For now, just staggered. Okay? Let's work on this first. Okay. When they're right on top of each other, what do we call the sun being on top the moon? Eclipsed. And so what are we going to call them when they're on top of each other? Eclipsed. Yep. Okay. You all are, except for you, eclipsed, right? You are staggered. Because you're staggered off of everybody. Well, him, except for him. You're eclipsed him. Okay. All right. Is that making sense so far? Fantastic. Okay, so remember these staggered conformations will be the more stable conformations in this case. Okay? If you have something that was to attract on these 2 positions, we'd actually flip this, wouldn't we? Okay?
So staggered is the more stable for
Yes. Yeah. And we can see that right here because the potential energy is the lowest. Keep in mind this is not 0. Okay? This has potential energy. It is not 0. It has a potential energy. Okay? This just is higher. All that matters is relative potential energy. Notice the scale says nothing about 0. Okay? Okay. See, there's no potential energy 0 on here? Okay.
Is staggered usually the most stable form
Yes.
for most compounds?
Most compounds, some form of staggered will be your most stable form. Yeah. It's unusual for it to be anything else. Because most compounds you're going to look are going to be nonpolar bonds interacting and won't have high polarity, which would give you like a negative and a positive, right? So most of them are just going to be negative electron clouds interacting. Yeah. But out of my 30 publications, I have 3 or 4 of them where we have a counter case in it. Okay? But that could just be because I did things that were unique. So, overrepresentation. Okay. Again, this one's repeated patterns all the conformations are going to have the same energies. Okay? Please note how many of the conformations do we have here? Okay, I have a 4, a 2. Any other? 2s? Most people are 2s. We got some 4-ish. No? Okay, let's count them. Okay, so we can count either the transitions or we can count the lower part, right? Which is the conformations. And so we have 1, 2 right there, but we have the hints of something else here, don't we? And what do you think that one would be if you let it go all the way down? That would be the third conformer. Okay? There's 3 conformers. Yeah. And those are literally the lowest energy minimums. Each one of those is conformers. You can actually tell this because you can go 360 degrees. How many staggered would there be in 360 if they happen every 120 degrees? It'd be 3, right? Yeah. So there you go. There's one at 60, one at 180, and then there'd be another one. Difference between 60 and 180 is 120. And so if we add 120 to 180, it's 300, right? We try to add that again, what do we get? 60. Okay? I know, right? Yeah, that one's zoomed in for an arbitrary reason, by the way. Does anybody have any questions so far about that? So conformations are actually going to be important for organic chemistry as well as isomers, which we had talked about previously. Remember that? Mm-hmm.
So, if we were given that chart on the top, we would have to say that there were 3 complements.
I mean, that's not typical. Like, the questions I'm going to ask you guys are just like the homeworks. So, the way to figure out what sort of questions you're going to see is to do the homework. Yeah. They're going to be just like it. I'm not like weird random questions that you guys have never seen anything about. That's not going to happen. I gave you homeworks because I thought they were representative problems that would cover the material in your book and make you understand it better. I give you tests to see if you understand that material. Like, there's nothing surprising about me. I'm boring. It's very straightforward. Maybe challenging, but it's very straightforward. I like to say that I am tough, but I'm fair. Okay? You can never say it's not fair. It's fair. It's 100% fair. It's absolutely the definition of fair. It's just horrifically tough. Be accurate, dang it. You can call me a jerk, but you can't call me unfair. Hell, it's even automated. Okay, so remember now we're going to propane. Now we have another CH3, right? Okay, we have another carbon. And so now we have 2 bonds, in which case we could rotate around, don't we? So we have 2 places that we could have different conformers. Can you see that? We have one, which is represented here, right? And that's going to be the one we're going to look down first. But we also have this one right here, don't we? Okay? Now, when you're talking about conformation, you have to talk about it 1 bond at a time. It's not going to make any damn sense to try to say both of them at the same time. Okay? Okay, so the first one we're going to look down is C1 to C2. That C1 to C2, do you know how you number the carbons here? I taught you. It's the same way as we talked about in IUPAC. It's just the IUPAC numbering. In this case, is there any reason I numbered this one 1 and this one 3? No, it's arbitrary. Yeah, in fact, it's the same thing either way in this case. Okay, so again, we look down this. We have a Newman projection. The front carbon has all hydrogens like it did before, right? This rear carbon, hey, what happened to one of the hydrogens? It's not hydrogen anymore, is it? It's substituted. And so instead of a hydrogen, we're going to draw in a CH3. So one of those places on the rear carbon has to have a CH3, a methyl group, right? Notice we do not try to represent any three-dimensional structure down here, nothing. Okay? Was that the question?
No, I was making sure that I was thinking about this right, because you just explained it, and when you started talking about the graph, but it was just the tetrahedral. I just wanted to make sure I was looking at a three-dimensional.
Oh, yes, these are all tetrahedrals because they're all going to be sp3 hybridized. Yeah, because they have 4 different domains, directions to hold electrons in. Okay? And that's every time you have 4 bonds on a carbon, it's always tetrahedral, always sp3 hybridized, because that's literally 4 bonds means 4 directions for electrons to be in. Did that help?
Yeah, I was just like,
Yeah, you always get repeat. Okay, remember how we talked about the line edge and you make a zigzag? That's literally representing the tetrahedral shapes. Tetrahedral shape causes it to go up, and then back down, and then up, down, up, down. Yeah.
is that what most hydrocarbons will be?
Yeah, anything with single bonds is always going to have a repeated tetrahedral shapes. And in fact, most things that have single bonds, even if it's like oxygen, will have an overall tetrahedral shape. That's why like H2O is bent, right? Because the lone pairs take up that space. Okay, did that make sense? And make sure I actually answered the question. All right, so please be careful about this. This is one of the #1 places for students to start making mistakes, is they try to make this CH3 down here 3-dimensional. They try to put in another Newman projection. They try to get fancy with this. It's not. You just collapse down everything else that's on here except for that bond. Okay? So it didn't matter if this is a CH3. This could have been a C6. It could have had 6 carbon chain on here. We don't care. Okay? Hell, if you wanted to not have to like draw out what's on it every time, you could put R prime. There you go. It's an R group. It's a residue. I don't care what's there. I just need to represent it so I can know it's different, right? Okay? Okay, so again, keep that in mind. It's not important that exact structure down there, okay? If it happened to be a ring, you could put like a ring shape over here, and it connects back over, okay? The exact 3-dimensional structure there doesn't matter. Newman projections, we're just looking down that one bond, right? And discussing the conformations down that one bond. Okay. It again is going to have that same pattern of eclipsed to staggered to eclipsed, right? Okay. Okay. What you will notice though is there is a distinct difference between some of the staggareds here. Okay? We're only seeing one of those conformations here, but notice that in this staggered here, we're going to have a rotation that involves this CH3 crossing things, right? Okay. Okay. So we're going to, again, get a repeated pattern with the same energies. That difference in energy, though, is going to be larger because that CH3 is bulkier, right? Okay. Can everybody see that you still have a CH3 here, so when you rotate that on the front here, you still have hydrogens in each of those positions. So again, you get that repeat 3 degenerate conformers. The only difference from the previous graph is that this right here is going to have a larger energy difference. Because trying to rotate that bulky group around is going to take more energy, right? Okay. Does that make any sense? Fantastic. Okay, so this right here is butane. This is where we're going to start getting a bit more differences happening. Okay, so we're going to look down the middle bond for the butane, 2 and 3. See that? So C2 to C3. And we're going to represent that with a Newman projection down here. These Newman projections correspond to these three-dimensional structures. Okay? Okay, so what we see is right here we have the totally eclipsed. This is going to be the highest energy transition state. Why is this the highest energy? Come on. Yeah. Yeah, the two CH3s, the two methyls, right? They're the bulkiest groups, and they're eclipsed in this case, aren't they? And so that's going to be like two really big guys trying to sit together next to a plane, right? Never works out quite right, does it? One of them pop out. Okay. It's like trying to squeeze two large balls into a container, right? Boom. High energy. This right here is the gauche. This is a staggered form. The gauche form is going to be a 60-degree offset from your large groups. Okay? We call it gauche because has anybody ever heard that term before? It's a French term. Typically you hear it like art. Yeah, this is so gauche. Right? Okay. Actually, I might be wrong. That might be German. I'm going to have to look that up. I forget. So basically like 1930s, it was like French, and then the Germans took over on chemistry. A lot of the stuff for organic chemistry is actually German. Interesting side note, Blitzkrieg warfare happened because of chemistry. They used to feed the soldiers meth so they could stay up for 3 days and run along with the tanks and stuff. Yeah. Which is one of the reasons the Nazis were so fucking crazy. It was a form of meth that they were taking. Yep, methamphetamine. Anyways, so keep that in mind. Again, we have subcategories of staggered, right? The form where the two large groups is 60 degrees apart. There's two of those forms, one on each side, right? So there's one on this side as well. Okay, those would be gauche. This is the eclipsed form. Notice the difference between totally eclipsed and eclipsed. Okay, this has a hydrogen eclipsing one of the large groups. This right here is the anti-form. Okay. Your book calls it anti, and that's fine. I'm going to teach it to you as anti. There's also, you can call this cis. Okay? Okay. I mean, you guys have heard cis quite a lot lately. So, yeah, feel free. Cis means opposites. You guys know that. Anti also means opposite, right? Both are correct. Both are the correct terminology. Anti technically would be slightly more correct in this case, but there's not a lot of difference. Okay. Again, anti is the maximal separation staggered. If you were to look at this in terms of how much energy something has, would this be the most stable, second most stable? What? This one?
Yeah, out of all 4.
Yeah. Most stable, right? Because it's the most separation between the large groups. Okay? How about this one? Second, well, yeah, kind of the same thing, isn't it? Well, yeah. This is the second most stable. Technically, this one would be the second to least. Yeah. This would be a transition state, though. So these are two conformers. And then this would be the highest energy transition state, right? That's the least stable. Yeah. Second least stable. This is actually stable and will actually show up for most compounds. This would be your most stable form, right? So in terms of stability, when we talk about that, that also means the conformer you would see the most, right? So like at room temperature, you would see the anti-form the most, okay? What would happen if you increase temperatures, by the way? You get more of the less stable forms, right? Okay. Decreased temperatures, more of the stable forms. Okay, so this is the full conformational analysis for that butane, corresponding to their Newman projections. Again, please note that it is a mirror image. See that? Okay. This right here being the most stable form. There's only one anti because they're opposites, right? As you go from the 0 to the 180, one side is the exact same as going the other side. The 180 to 360, right? Okay. And again, remember that this comes back together there. So this connects to here. Does that make sense? Okay. Or another way of saying that is 0 and 360 are the same thing, right? Okay. Okay, so again, right here we have the anti-conformation. This would be the transition state which you have to go through. That's the lower energy eclipsed, right? Then this right here is going to be one of the gauche forms. These gauche forms would be referred to as what? So we have two gauche forms here. They have same energy, and so they're called they're degenerate. Okay? But they are two distinct conformers that are degenerate in energy. Right? Like if you were to look at these molecules, you would have both of these forms in that sample. Okay? You just can't tell the difference between them because they have the same energy. And effectively, in this case, they're the same thing. You don't really care. This right here is actually literally the same thing, right? There's not two of these. There's only one of these. Because that has those two methyls lined up. Okay? Okay. Does that make sense how to read those? How to understand that? Okay. You kind of have to be careful about what is degenerate, but exists in two forms. Okay? Versus what is the same form. There actually is no difference at all, right? Okay. Like, for example, these have two forms, but are degenerate, right? Okay. Okay. Does anybody know why that might be important? Okay, what if I say I have 1, 2, 3, 4, 5, 6, 7 degenerate desks? Does that mean there's only one desk back there? Certainly hope, because you guys would be really stacked up, wouldn't you? No, I have 7 desks, 7 populated states that are degenerate, right? Yeah. And that's similar to this. Whereas these, I have one desk up here which I'm sitting at, right? And that's it. No other desks are degenerate to mine. Okay? Okay. Is that making sense?
Degenerate is the same energy.
Same energy, yep, but they still are separate orbitals or separate places. Okay? So they exist, but they have the same energy. Yeah. Many people get that confused because degenerate also typically means we can't see it. they have the same energy, then you can't really separate them or do anything with it. Yeah. This right here is steric strain. This is actually your force that keeps these from wanting to overlap. Okay? So, again, this is that totally eclipsed form right here. Remember that because this totally eclipsed, what's going to happen is every single atom always has a cloud of electrons around it, right? And this is why they don't typically come in contact. Okay? Otherwise, if you can actually smash two of these nuclei together, like in a star, you could fuse them. Yeah. Or cause them to split, depending on where they are in the periodic table, okay? But, yes, that doesn't normally happen, does it? Why does that not normally happen? Because they have electron clouds around them, they repel each other, they take a tremendous amount of energy to actually come together, don't they? Okay? And so this is what you're seeing, those electron clouds interacting and repelling each other because they're too close. Okay? For things larger than hydrogen, this can actually be quite a distance, by the way. And it gets a bit more complex because these orbitals take on some kind of weird shapes. Okay? But for hydrogen, they're just nice spheres, aren't they? Yeah. All right. So, again, that steric strain or steric hindrance is that interference when you're talking about two bulky groups like we are right here. Okay? So what causes that difference? What causes those transition states to be so high energy? You can say steric hindrance, okay? Or steric strain. These would be the conformations of higher alkanes, longer chain alkanes. Again, remember you're going to have the gauche and anti-conformations. Those are the only stable ones, and so those are the only conformations. Okay? This would be the all anti form, and that's how we typically draw these, right? Just know, yes, that would be the most stable, but that doesn't mean that's the majority of your population. Okay? Okay. You're going to have many, 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 many gauche forms. Okay? Okay, so this is your cycloalkanes. As you see, here we have the three-membered ring. Why do we start at the three-membered ring for cycloalkanes? Can you make a circle with less than 3 points? Any shape with less than 3 points other than a line? No, no. 2 points makes a line, right? 1 point makes a point in space, that's it. So the minimum you can actually close back around is 3. Okay? And so that's cyclopropane. 4 would be cyclobutane. 5, cyclopentane. And you got the pattern there, don't you? Okay. All right, these are some of the physical properties of the alkanes. It's going to be non-polar. They're relatively inert. They don't react with a whole lot of stuff. Though, to be fair, relatively inert does not mean you can leave this sitting around a lab and nothing's going to happen. Okay? Anybody ever had something that's like really old and it's rubber? Yeah. What happens?
It's like really dry.
Oh, you haven't had it really, really old then. So yes, it dries out typically at first. But if you wait long enough, like 20-something years, 30 years, it actually like goes back to being almost hydrocarbon-like, right? It goes back to a semi-liquid like tar, and it'll start dripping out. And so there's a form of hydroxide free radical in the atmosphere that typically catalyzes all these reactions. So if you leave a hydrocarbon sitting out, you'll get tar. Okay? Anybody know where tar comes from? Okay, so sometimes things die under pressure and a little bit of heat. What do they turn into? Hydrocarbons. If it had enough oils in it and shorter chain stuff, they'll be like petroleum. If they have a lot of larger compounds, then they can form things like coal, right? Okay? What do you think happens if it was without oxygen before? And that's how you got the hydrocarbons and petroleum, right? Fossil fuels and everything. And then all of a sudden, an earthquake happens, and now oxygen gets in there. What do you think is going to happen to it over the course of a few thousand years? It's going to get oxidized. And that's how you get tar. Okay? Same thing happens if you leave gasoline out. If anybody's ever done that, had like a really old gasoline container or some of the bottles in lab. Touch the outsides, they're really sticky, right? Yeah. Anyways, so keep that in mind that yes, relatively inert means they're not going to immediately react with stuff, but they're not so stable you can just leave them out forever and be okay. Okay? Boiling point and melting point are going to depend on the molecular weight. Again, the longer they are, the higher the melting and boiling points are, right? Okay. This is the cycloalkane nomenclature. So your cycloalkane is going to be your main chain. Alkyl groups attached to the cycloalkane will be named as alkyl groups, just like they are in the rest of the IUPAC naming system. If only one alkyl group is present, then you don't need a number, because it can be assumed to be the first position, right? Okay. Remember, if it's a circle, where's the top of a circle? Anywhere you damn well want, right? Any point on can be the top, can't it? Okay. Same thing with rings, right? So right here I have a single substituent. That's a methyl. So it's methyl cyclopentane. I don't have to put any number because I can just always assume that's 1, right? It is correct formatting to put that on the top so people see it first. Okay? But that's a polite thing to do. It is not this has to be that way. Okay? You could have also put it on the bottom, side, whatever, I don't care. Okay? I get a lot of people that ask me that. Okay. Again, here we have a cyclohexane. We have a complex alkyl group here. And so we need to use the complex alkyl group naming terminology, right? So we put parentheses. That is a 3-carbon chain, so it's a propyl. And on that propyl, we have a carbon, a methyl group on 1 and 2. So that'd be 1,2-dimethyl propyl cyclohexane. Notice again, we don't number these because we only have one substituent on the cyclo, right? Okay. Anybody have any questions so far? Fantastic. Okay, so again, this is the cycloalkane nomenclatures. If you have 2 or more substituents, then number your main chain so that the substituents will have your lowest numbering possible. Okay? So one of them will be 1, the other will be 2. The way you number these is you do the highest priority as 1, the most things, substituents, get the lowest number, right? So for example, ethyl in this case has a higher priority than methyl because it's larger. Okay? More molecular weight. And it's going to have a 1 there. We'll give the 2 where the methyl is, so it has the lowest number possible, right? Keep in mind you could have went 2 over here, right? But that would be incorrect, because that would give methyl a higher number. Okay, so over here we have 1, 2, 3 things substituted. So the 1 goes where we would have 2 things as 1, right? Okay. Otherwise, we'd have less low numbers. Okay, and over here again, we have 2 substituents over here. And so we name that 1, 1, right? Okay. No, you're good.
It's just in the ones that are 2 acting as 1.
Yes, so we have 2 substituents. You want to minimize your numbers possible on as many substituents as possible. Okay? And this gives you 2 1 positions rather than 2 4s. Does that make sense? Fantastic. All right. So the cycloalkane will become a substituent when the alkylic portion of the molecule contains fewer carbons than the cyclic part, or when there is more important functional groups on that molecule. So for example, we have a longer chain here on the straight chain portion, right? And so that becomes the parent. And then the cyclic portion becomes a substituent. How do you name any alkyl as a substituent? You change ane to ile, right? Same here. So the substituent form of cyclopropane is cyclic propyl. Yeah, so cyclopropyl, right? Okay. Anybody have any questions there? This one's a double chain. Ooh, so impressive. So this one right here ends up being cyclopentyl, cyclohexane, right? 6-membered, 5-membered. Okay. These right here are geometric isomers. So remember, isomers have the same formula, but different structures, right? Okay. So geometric isomers, the only difference between those is how they are arranged geometrically. Okay? Okay, so the first thing I need to mention here is geometric isomers are not conformers. I know that this looks a little bit like the conformations we just talked about. Like some of you might be tempted to go, oh, isn't that eclipsed right there, right? I mean, yes, it is eclipsed on top of each other, but that is not a conformer. Okay? So it's not the eclipsed conformer. The difference between them, remember the definition for conformers. So that has to have a bond which you can rotate around, right? Okay, so one finger rotates easily, right? No problem. Yep. 2 fingers together. Everybody do it with me? So one finger rotate, no problem, right? Everybody's good. 2 fingers try to rotate without breaking. You can't rotate, can you? Yeah. They never actually rotate. You'd have to break one. Okay? And so when you have a double, triple bonds, these sort of things, or rings would also do it, right? If we do a ring, can we rotate one of our hands so it points the other direction? No, we can't we? Yeah. And so that's where you start getting things that diverge from conformations. They can't rotate around freely, can they? It doesn't matter if you provide them energy, it can't rotate unless you break a bond, right? If you break a bond, you're not doing a conformational change, you're doing a reaction, aren't you? And that's just by definition. Okay? Okay, so these are isomers because they're different compounds. To change from one to the other, we actually have to react one, don't we? Okay? Whereas conformations, we just have to provide a little bit of energy. Flip-flop. Okay. So this is the cis versus trans. Remember when I said you could also call cis versus trans? Yeah. So the trans would be I may have said cis. I did. Please go back into your notes. It's trans. Yeah. I didn't realize that I said the opposite thing of what I meant to say. Yes, so please go back in your notes. That's trans, opposite sides, cis being same, right? Man, I even said meaning opposite. Nobody. Okay. Uh-oh. I've definitely indoctrinated you guys. You guys know the sky is red and green, right? Up is down, down is up. We're going to go full 1984 here. Okay. You guys are getting so indoctrinated. Okay, come on. When I say stuff like that, I go, Dr. Clausen, I don't think that's right. Because, I'm a human too. I go dyslexic sometime, and, Flip-flop switch. Okay, anyways, this is cis. Cis means same side, right? And in fact, if you're having trouble remembering that, cis, same side, they have a symmetry to their names, right? And then trans means different, right? Opposites, okay? And so right here we have a cis isomer. They're the same side of the double bond. Here we have a trans isomer. They're different sides of the double bond. This is the simplest way of talking about these isomers, okay? There's a more complex way that has more rules that we're going to get into. You may have noticed we can only have two things here, otherwise this entire naming convention falls apart, doesn't it? Okay? Like if we had three CH3s, how do you tell which is which? You can't anymore, can you? Yeah. Yes. This can also happen on rings. Right here we see an example of the rings. Cis again, same side of that ring, right? Trans would have it on opposite sides of the ring. Okay? Okay. Again, remember this is relative to each other. Okay? Don't forget these things flip-flop and rotate in space all the time. There is no actual up and down for these molecules. Okay? Okay, so the stabilities of your cycloalkanes. When we're talking about cycloalkanes, you may have noticed that when you get down to these 3 and 4 membered rings, right there, what sort of bond angles would those have between those carbons? So see how it goes like that? That'd be a 60, wouldn't it? Yes, I'm sorry. 120 with 60-degree splits, yeah. So yes, 360 to get all the way around. So each of these bond angles needs that 120, right? And that means that it is definitely not that ideal 109.5 degree split that we would normally have. What is it? So we have highly perturbed our normal bond angles, haven't we? What does that mean? We're going to have a lot of strain from holding that bond angle in that way, right? Okay. What about these right here? 4 carbons. Okay, what does a square have for bonding, for angles? 90. So these are 90 degrees, right? Yeah. This part has 60, by the way, in case you're curious. Okay. This part would be the 120. Yeah. Okay. 120 degree offset. Bond angle is actually 60. Just to be clear. Okay. Okay, so again, what we can see here as we get to the 5 and 6 membered rings, we actually get very close to the 109, don't we? Okay? And then once we get past the 5 and 6 membered rings, then again we have to diverge and get larger bond angles than 109, don't we? So that we can fit everything in. Okay? And that causes what we call ring strain, right? Or another way of saying this is angle strain and torsional strain. Okay? So again, remember that when we have all single bonded carbons, that's going to have a hybridized carbon. That means there's 4 objects, 4 domains in space. The ideal separation between them is 109.5, right? And that's what we call the tetrahedral shape. That happens because the bonds repel each other, right? Okay. So any deviation off of that angle means you have to bring things that repel each other closer than they otherwise would want to be, right? Which is going to be strain. So when a cycloalkane carbon has any other angle than 109.5, we can term that as angle strain. That's a difference from the optimal overlap, which is again 109.5, right? So there's other terminology for this. It is very rarely used. I don't think I've ever actually seen it used in any actual paper. And I have 30 publications in the field, and my advisor had 1,000-something publications in the field, and I never heard him use the term, not once. Okay? And so Bayer strain is actually the named version of this. It is, yeah. Okay? I've never actually seen it actually used, though. Anyways. So torsional strain is what arises when all the bonds are eclipsed. And this is also going to happen in these rings, because we don't have the freedom of motion like we did in the single bonds, right? Where they can just flip-flop everywhere and relieve this torsional strain, okay? You can't get perfectly anti when you have these things trapped together in a ring. And let's see that. Okay, so first off, here we have the angle strain, right? For a four-membered ring. We've compressed that 109 it wants to be down 19.5 degrees, so that it's only 90 degrees now, right? And that means that the electron clouds from those two bonds are going to interact more, aren't they? Okay, and they'll repel more. And so this wants to break apart from that. This right here is the Newman projections. See, there's two Newman projections looking down these two bonds in the ring here. See that? Okay. And what do we see here? Well, they actually have to be eclipsed, don't they? Okay? And there's only so much you can do to relieve that, because this ring can't really twist that much, can it? Okay? And so these are going to cause that to again have our torsional strain. That's the torsional strain part on the right. This right here, angle strain, torsional strain. Okay? Now in reality, we're using this four-membered ring and we're talking as if it's a perfect square that's flat in space. This is going to twist to try to relieve those. Okay? And so in reality, this becomes a bent shape. This is actually going to bend, like you folded this like a piece of paper. Okay? So it's like going to fold along this line here. And it'll be bent. And that's to try to relieve some of this. Okay? It won't be perfectly possible because, again, it's just too trapped, right? But it will bend. Okay, let's talk about some heats of combustion. So the heat of combustion is going to be the amount of heat released when a compound is burned with an excess of oxygen in a sealed container. This sealed container is called a bomb container. Notice, by the way, the terminology here is the same as bombs, as in like, I made a bomb and bombed someone. Okay? And in fact, the reason this became extremely popular after World War II, can anybody guess? What would have they made a lot of, and then the war ended? Bombshells. And so they literally cut the bombshells, put a threaded connection, and made bomb calorimeters. And so you literally used to use a bomb, like a bomb that would be dropped out of a plane. Because that's what they do, right? They maintain the heat and pressure inside a bomb. And normally a bomb would fail and blow up. But in chemistry, we just don't cause it to fail, hopefully. Anyways, so this is how you measure heats of combustion. If the compound is extra energy as a result of the ring strain, that energy is going to be released in the combustion because you're completely disassembling it. And that will cause it to release an excess of energy than the straight chain form. Okay? And this can give us an idea of that difference in the energies due to these two factors, which we call altogether ring strain, right? Okay, so this is your torsional strain again. We can see in the 3-membered ring, this is really drastic and we can't do absolutely anything about it, can we? Can you move the 3 points in space to do anything other than be flat? No. Anybody know why that is? How many points do you have to have in space to define a plane? 3. 3 is the minimum number of points to define a plane in space. Okay? And so if you have 3 objects, all you can ever be is flat. More than 3 objects, you can now be something other than flat. Okay? Okay, we'll pick up here next time. You all have a great day, and I will see you on Thursday. Don't forget, lab Thursday. The lab notebooks are coming up very soon. Okay? Yes, yes. I would recommend getting them into me like Thursday, Friday. Okay? I would actually recommend trying to turn them in during your lecture here and have them done there. And that way, if you like miss it for something, you still have Friday to get it in under my door.